And this time I should really acknowledge the people who do not think only about the concepts, but also do the work. This is Michael, Sebastian, Carsten. And before Tina, before he went to Nottingham, he was involved in the beginning in Weibin. Weibin actually did most of the calculations for the trilobite states you just heard about. And I just wanted to make 2 or 3 remarks about that, because I think Tilman never mentions he's so modest what kind of accuracy he achieves. This is mind-boggling, and it's totally daunting also for theory. So this is again for his, ultra long-range molecule. That's the distance between these 2 nuclei, 1,000 atomic units, 2,000. You see at n equals 35 roughly. So this is next Rydberg manifold, n equals 32 here, I believe, or 33. And you see this is gigahertz scale. So this is already very, very, very small, if you wish. But the actual spectrum he showed you is on the thickness of this line on 100 megahertz. Yeah? And the way how to calculate that, we didn't know at all how to calculate that in the beginning, because it's so highly excited, there are thousands of states below, right? So you cannot really do full calculation. Brute force doesn't work. So you have to find something. And then again, of course, this is not a trivial hydrogenic kind of Rydberg spectrum, because if the 2 atoms come together, there's a non-trivial situation there at the origin. And you don't know what to do. And there comes now this cliff here, where it goes almost 3 orders of magnitude down compared to the 100 megahertz here, where your energies sit. And this makes a very funny situation. So I thought, okay, let's just invert scattering theory. So we scatter basically inwards. We have our bound state sitting here. Here it's bound, basically on the outside. I don't know if I have this here, maybe not. And here we say it's just free. It can go. In reality, the 2 atoms come together, but we just forget about it because the system decays then anyways, the whole molecule, if they really collide, the 2 nuclei. So let's do scattering theory inward. And if you don't really know what to do, then you do the most primitive thing, and this is you put the system in a box. Yeah? So we put it in a box here and out here, just a rectangular box, and then calculate basically the spectrum as a function of the size of the box. So we put this boundary closer and closer to the origin. And this you see here, this is basically where the position is of this inner boundary of the box. And here you see now these vibrational energies, these eigenenergies, these are the resonances. And this is, again, I think what Tilman mentioned. What you can see here is you have kind of very narrow avoided crossings, because when you make your box wider and wider, then excited states drop down. Yeah? They come, of course, lower and lower in energy because the potential is wider. And what stabilizes here, that this is also called stabilization method, is essentially your resonance energy. Although you calculate only bound states, which is relatively simple. And this is then what you showed you. So here's really his accuracy, right? Megahertz. This is like 50 megahertz where all the lines are. And what I wanted to tell you is that, of course, these were our comparisons in the beginning between theory and experiment. And you see this was not so nice because we missed a lot of states. A lot of peaks they had, we missed. And we didn't know if their peaks were right or if we're missing them because it was really new territory. And also in the beginning we didn't understand this one was really the trimer. But okay, after a while we were quite certain that this is really the trimer, basically twice the energy of the main dimer line here. You see that? 22, 45. This is always measured from the Rydberg main line here. And then you think about it, okay, let's take it seriously with this trimer. So the trimer is this one. It's kind of the sum of 2 bound dimers, right? So this is twice basically the dimer energy here. But the dimer can have excited states. That's all the states we see here. So why not have other combinations of excited, basically bonds in the trimer? Now let's check that out. So here's basically 2 times the ground state. And here you see the excited state energies. And sure enough, the missing values here are very much fitting, essentially combinations of excited dimer states. B1 and B0, B1 and B2. Here, here, and here. So this one we didn't see. So we didn't calculate that, right? This is just a combination of the dimer lines, but we are pretty certain that in the experiment they also saw excited trimers. Anyway, so this was only a comment. And the last one is this quantum reflection. This is really, really crazy. And so this is again this potentially showed you, yeah, where this cliff goes down here, these 3 orders of magnitude. And essentially these are the normal states, the ones we knew before, like normal vibrational states in this last slope of the wave function. And here are these new ones, all the lines we just were discussing. And they're really living basically from quantum reflection. And what that means is here sketched basically in a rough way with box-like potentials. I try to kind of sketch how the real potential goes. And you see here would be living the normal vibrational states, and the ones we're discussing, they are really living here on this plateau. And the funny thing is, the wave function of these states, and you saw that here, they do not penetrate into this interior space because they are quantum reflected here at this barrier. So they're sitting at a classically allowed energy, but still the motion does not go inside here this classically allowed region, and this is really quantum reflection. And this actually does only work because here is a sink. If the 2 atoms come together, I told you, then the whole system gets destroyed, it decays. And that's important, so this is like a free boundary. It's not normal when 2 particles come together, this is like a free boundary, like if particles go to infinity, but here it's the case, at least for the system, because the system gets destroyed. And only because of that, this quantum reflection really works in that way. If there would be another reflection here, because the wave comes back and it's not just absorbed, then this quantum reflection phase would not work like this, because you would have an additional boundary condition here. And this is actually the case for normal tunneling and things like that, but that's a different story. Anyway, so this is what I wanted to comment on, and just keep in mind how accurate this whole thing is. This is really, I mean, on a 10 to 50 megahertz scale, several lines measured. Hey, and calculated. Okay. So, what I really wanted to tell you about in the 3rd lecture, finally, is now the excitonic motion really taken to Rydberg gases. We will discuss a little bit coherent atomic motion. And this really refers to this electronic transport through Rydberg-induced atomic motion. And we will go from single Rydberg atoms to atom clouds, also using the interaction blockade in the end. And also, I will use in the end a little bit the scheme of Rydberg dressing to transfer Rydberg exciton properties also to ground state ensembles. And you will see that has kind of a surprising effect on the entire ensemble of an atomic cloud. Because this allows you coherent mechanical motion then of the entire cloud. So this, you know, we are very familiar with by now. This is now really again our dipole-dipole interaction, the full Coulomb interaction, but everything is neutral for large distance of, let's say, an Rydberg atom which is in an S state, kind of here sketched as circular, and let's say a P state. This is our model we will use, and this I will refer now to as the excitation. Remember, I told you always molecules in ground state and the other one in the excited state. We only took 2 states in the 2 past lectures. Now we transfer that to atoms, and basically one atom is with respect to the exciton excitation in the ground state, but this is a high Rydberg excitation, so don't get confused. It's standing NS Rydberg excitation, and what corresponds to the molecular excited state or unit is the NP Rydberg atom here. This I call really excitation. And of course the interaction is the same as we know. If you expand that for large distances between the atoms, we get basically this dipole-dipole interaction term. And this is exactly our exciton coupling. And I was asked that before, I mean, are there permanent dipoles? Of course not. There's no permanent dipole, as you see here. And therefore the expectation value would be 0 of this term. But there's a transition dipole. So of course you have to go from NS to NP, and for the other atom from NP to NS. And then this one is not equal to 0, and this really contributes to the excitation transfer. So here's now, again, schematically our situation. And we will consider really these Rydberg atoms in a one-dimensional chain. So for all of the talk, make it simpler. And So here I took 1, 2, 3, 4, 5. Yeah, so these are the NS states, atoms in NS states, Rydberg states, and this is our excited one, quote unquote, which is in the NP state. And of course, we also have some at the ground state. And the vector, capital R, contains now basically the positions on the one-dimensional line here of all these 5 atoms. So it's a 5-dimensional object or vector. Yeah, and our electronic state we describe now in this way. Let's say pi 4, just to indicate that all of the atoms are in the S states, but the fourth one is in the excited state, that is in the P state. So pi 1 would be if the first one is in the P state and the other one's in the S state. The fourth one here is the excited one. The Hamiltonian you know already from the last 2 lectures. This is the kinetic energy of our atoms in this 5-dimensional space. And here's the electronic Hamiltonian, which is simply the dipole-dipole interaction and all the discrete, basically, states here. So that's the dynamics we will be dealing with now for the rest of this lecture. We have a diabatic kind of physical interpretation because these are really kind of the atomic states. And you can just, of course, take basically coefficients which depend on the respective position of all the atoms, like linear combination, and this would be a suitable basis to diagonalize or represent your entire system. But of course, we know this is not the exciton basis. The exciton basis is the adiabatic basis. Yeah? If you keep the distances between your atoms fixed, and just diagonalize the electronic dipole-dipole interaction. This is our electronic dipole-dipole interaction matrix here. This we also had before, at least for 2. A dimer here. Now we have, of course, 5 atoms. And we can now diagonalize that and see how this looks like. This is shown here. So this is now essentially, basically, our 5 sides and the 5 different adiabatic exciton states on these 5 atoms. And you see here the different amplitudes, plus and minus. So this would be the first exciton state. You see this is relatively homogeneously excited on all the sides, a little bit different. The next one is 2 negative amplitudes, 2 positive ones, nothing on the middle. Then this one, here again, of course, nothing in the middle for symmetry reasons, and so on. So these are now exciton states, and it simply emerged from diagonalizing this matrix we just saw here. And these coefficients here is basically then, if you wish, this matrix altogether. So the 5 states K, here it's N, and basically their components M on the individual atoms. Now, for the first time, we let these finally atoms move, right? They move. And of course, if they move, it's the force here which will be exerted on them, right? So moving means we really fulfill here the kinetic energy and solve then in the end the basically, if you wish, vibrational Schrödinger equation. It's not vibrational because it's free motion, but the motion of the atoms with this force exerted by the dipole-dipole interaction. And now we can see how this would work. So this is shown here. This is as a function of time. And here, the horizontal, vertical story is really the position. You see R in micrometers where they start. They start here at equal distances, at time equals 0, and then they start to move. When you see here, the force is like that this is attractive here, so they all move to the center. And you see, we stopped here calculating simply because we only took one channel. And of course, if they start to collide or interact much stronger, you would expect some transitions. That makes the interesting part we'll come to. But in this approximation, only taking one adiabatic channel, as shown here, this is not included, therefore it doesn't make sense to calculate it further. This is just to illustrate to you how these forces work now, really, on the atomic motion. And you see, of course, here it's different. Here these two attract each other pairwise. The middle one is not affected, stays. And again, these ones have negative signs who speak to each other, so repel each other, and so on. So they attract each other. Yeah. So this is basically now really how the dipole-dipole forces exert mechanical force on the motion of the atom. And the question is, if we want to make electronic transport, then we should localize the exciton. Right now you see it's completely delocalized over all the sides, right? Basically in all these 5 eigenstates. That's more or less what an exciton needs if it's completely coherent. So the question is, how can we localize the exciton? We can localize it through a defect, yeah? Breaking the symmetry. And this is very easy. Essentially, we move one atom closer here to the other 4. The first one we move closer to the other 4. And this then results in the following distribution now of the exciton. So you see here, this is now the probability basically to have amplitude on, or basically, yeah, the weight of each atom to carry electronic amplitude. And you see, if I move this relatively close, 0.2 of the normal distance between the atoms, so only 20%, then you see all of a sudden the exciton is only localized on the first 2 atoms with equal weight. And if I go more and more away to the normal distance, also x0 here, I reach the normal x0 distance, again an equal distance between all the atoms. Then I come back to my original exciton state. You see these two have the same weight. This one has a larger one, and this is of course our first exciton. Yeah, these two have the same. This is a bit larger. That's a bit lower. Okay, so that means by breaking the symmetry, by just moving one atom a bit closer, we can have a localization of the exciton.
Just to make sure I understand. So assuming we have a chain of atoms both in the S state or C, for example, specifically select one for the P state, with the excitation being immediately localized over atom or
Yes, if they are basically at equal distance, it will be localized immediately. You will see that later on dynamically that this essentially happens. It happens surprisingly fast. Okay, so now we know how to localize that, and we have seen that the atoms start to move, yeah, which is really what we want. And of course, they are very slow, so you can make our von Oppenheimer approximation, which is important. Otherwise, we would not be able to calculate that. And the potentials surfaces for the atomic motion are just the excitonic energies as a function of these distances. These are the excitonic eigenenergies. These are now the potential surfaces. And now comes another complication. I should have introduced you to that in the 2 previous lectures, but I kind of ran out of time for doing that. This is another technical point which is very important. We actually cannot compute the motion of the atoms quantum mechanically. This is basically too much involved, so we do them classically, like it's often done in molecular dynamics simulations. And for that, we use what's called a surface hopping formalism introduced by Tully, famous chemist, quite a while ago, and he proved in the meantime. And that means we basically calculate ensembles of trajectories for the atoms, yeah, according to a Gaussian distribution in the beginning, kind of operational wave function. And of course, the difficulty is if you encounter a jump to another surface, because quantum mechanically you would split. Part of your amplitude would go, let's say, on the excited state surface, and part would continue on the ground state von Oppenheimer surface. Now, if you do classical trajectories, that's not possible, obviously. So the classical particle has to decide: do I jump or do I stay? And this is kind of the whole thing of the formalism by Tully. This is shown here, that he found basically a consistent formulation to have a stochastic approach where one runs many trajectories and lets them jump to the upper one or to the surface where they were before according to a certain criterion. This criterion is shown here, and it's a little bit technical, maybe it's already late, so I won't go too much into the details, but essentially this is related, the probability to jump, to, of course, the avoided crossing between the two surfaces. If it's very narrow, it's easier to jump, and to the velocity with which you're approaching basically these avoided crossings between two curves with your nuclear wave packet. This is this R dot here. And the essential point is that on average, and this is Tully's fused switching algorithm, the probability for population of each of these potential surfaces with a vibrational wave packet corresponds to the average number of trajectories on the surface. So this is the consistency criterion one wishes. Okay, now let's check how well this works. And this shows you now also for the first time, if I have like 3 atoms in a row, I start with the 2 ones closer to each other, as I said in the beginning, so the exciton is localized on these 2 ones. And now I let basically the atoms loose and see what happens. And the point is also, now this is the comparison, and that's basically the whole reason why I show that between the full quantum mechanics and this Tully quasi-classical formalism, because with 3 atoms we can still do the full quantum mechanics. And that's a little movie. Well, it's not very ambitious, but you can see that here, hopefully. Yeah, so what you see essentially first, so the height is the amplitude. If there is basically probability density on this side, on this atom, oops. And you see also that the atoms move, So the first one collides, it's basically scattered back, and this one moves now to the third one, And if you continue, you won't see that, oops. Then this goes on, so fine. But the whole point of this little movie was to demonstrate that the red lines stay with the black dashed lines. You can't even distinguish them. That means that this quasi-classical Tully is quite good. And that gave us some confidence that we could go on to, of course, more atoms. It's kind of pointless to do 3 atoms. And this we can only do with the Tully formalism, so we don't have quantum mechanical comparison for that. So we have repulsion through the dipole-dipole forces, and that kicks these 2 apart, and then that happens again for the next pair. And this is now shown here for more atoms, so that's a chain of 1, 2, 3, 4, 5, 6, 7 atoms. And you see here again, this is the position. Maybe you can't see it so well in micrometers, separated by, I guess, something like 5 or 10 micrometers in the beginning. And this is again the same plot as I showed before, with essentially the probability of excitation now on each atom. This is the color code, and just watch the color code, how the electronic excitation really propagates through the exciton, through the atomic chain, if I let this run now. Oops. So here it goes. Oops, sorry. I wanted to stop it. No, here you see very nicely that really it jumps 2 by 2, So you have the excitation on the first 2, and a while later it's really localized on these 2 atoms. And there's almost no excitation on the other atoms. So it's really this exciton propagates through the atom chain, and you are right now here. And here you also see, of course, the mechanical forces. This is the path of the atoms. This one gets reflected backwards, repelled. This one, of course, forward. It kicks this one, and so on. Okay. And here in the end, you see, I think this was the question, what happens if I excite basically with the P, and then what happens to the whole chain? I think you see that very nicely here in the end, because in almost no time now the excitation is distributed over all the atoms, Because we don't have anything more to jump, we cannot propagate onward our adiabatic state, then it decoheres in almost no time, and basically you have then kind of a homogeneous excitation on all the atoms. All right. So the nice thing is, of course, this is not only excitation localized on these two atoms, which we have now propagated through the whole atom chain. But in fact, this is also an entangled state, because it entangles basically these two atoms with this one electron. Yeah? And the question is, of course, does this kind of coherent propagation, does this also transport this 2x2 entanglement? And this we will then investigate in a second. So here it's shown again the path, and now basically this like bright color here shows you how the excitation propagates, that you knew already. That's shown here again, a bit more maybe clearer. You see here that the population on each atom as a function of time. So in the beginning, of course, it's on atom 1 and 2, and then it goes 2 and 3, and so on, pairwise, as we just said. And afterwards, yeah, when the chain is basically exhausted, it settles on all the atoms almost in the same way. This is how it gets on all of them. And here you see why Tully works quite well, because this is essentially the fidelity, or this is how adiabatic the whole process is. So this is the population of the adiabatic exciton channel as a function of time, and it loses a little bit, but not too much. I mean, certainly not while the whole excitation propagates through the chain, only afterwards. And now comes the interesting part. So this is the entanglement. That's a measure of entanglement of formation, this is called. And this is for bipartite entanglement only. It's a simpler way. But here you see also very clearly, indeed, also, this is the green one, this entanglement is pretty much preserved. So that means our excitonic transport does not only preserve coherence, it also preserves entanglement, and you probably all know this little toy. But this is of course classical, where classically each ball kicks the next one and transports momentum and energy to the end, and then backwards here. And this is kind of a quantum version of this Newton cradle, where now, in addition of course to this classical momentum and energy for the atoms, the atomic motion, you transport pairwise, pair by pair, the electronic excitation coherently and the electronic entanglement, the pairwise entanglement. Yeah, so now just think about one chain is nice, but we would at least do the next step and would maybe just put together two chains. Yeah. So let's make a perpendicular one, and let's see if we can get the excitation around the corner or something like that. But then you see immediately, we will probably encounter a problem, because then we will have, even if we confine this to one-dimensional motion, we will have basically here a triatomic system. And remember, a triatomic system does not have only avoided crossings, it has conical intersections, right? Because it really forms a plane here. So that means we probably should first investigate a little bit what these ultra-cold Rydberg atoms do if they form a conical intersection. And then we asked ourselves, okay, let's look at the conical intersection. Does this occur if you have an ultra-cold gas of Rydberg atoms, as we all have? How likely is it that a conical intersection occurs? And this came kind of to our surprise. Conical intersections are absolutely abundant in ultra-cold Rydberg gases. How can you show that? Can show that in the following way. So you take a box and put there so many atoms in a Rydberg excited state, and then they have basically a small volume around them before they hit the next one, just the mean density. And you think, what is typical thermal fluctuations? And you simply now vary randomly the distance of each atom in this little volume, and see by variation of this distance of all the atoms, do actually conical intersections form. This is technically not so easy to really kind of be sure that conical intersections have formed, but there are ways to do that numerically. And if one does that, one finds, this is done here, that on average, if you vary basically, if you move around with your atoms up to here to the next neighbor, this is the full next neighbor, and this is half the distance and so on, that you encounter something like 4 conical intersections. Yeah? per atom moving. So this is really a lot. That means conical intersections should be quite important in these systems. If you look, of course, at this type of motion. Yeah, so what to do with the conical intersection? We all know that if you go around the conical intersection in two different ways, or if you encircle it, then there's this famous Berry's phase, and this would of course be a nice way to observe that. So we tried that. This is kind of a proposal for a circular ring trap for 3 atoms, ultra-cold Rydberg atoms. And to make this happen, one actually has to dress these atoms for getting the right interaction strength. But if you do that, then you can observe Berry's phase. Just to remind you maybe briefly, if you haven't heard about it, what Berry's phase is related to. It's again related to an adiabatic approach, and in the adiabatic approach then to the non-adiabatic coupling to other surfaces. And simply it states if you go around the conical intersection in a complete circle, then these non-adiabatic coupling matrix elements lead to the strange effect that basically your wave function acquires a phase of pi. This is like a Hamiltonian effect with the magnetic field that's very similar through adiabatic transport. And this you can now try. So this would be our conical intersection here. I just showed you. So this one between the upper surface and this middle surface, here is the conical intersection sitting. By the way, again, like so often with Rydberg systems, this would be a way to make a minimal model of a conical intersection. In a molecule normally it's very dirty because you have many channels. Yeah? And somewhere between 2 channels there's a conical intersection, others are close by. Here you can construct it in such a way that you have only 3 surfaces and 2 of them really show a conical intersection. That's the minimum you can get. And now we start basically here our wave packet, and we start our wave packet which has 2 components. One is running in that direction around the conical intersection, which is sitting here, the other one in the other direction. And of course, since they allow it's like moving wave packets in 2 directions, it has a nice interference pattern. And we see now what happens to this interference pattern if they come together again, these 2 components. And you see here, this is the original one, and part of it went around the conical intersection, part of it, of course, did not go around, but stayed on the surface. And the one part which went around actually really shows this pi phase shift. So this would be a very nice and clean way to demonstrate Berry's phase with ultra-cold Rydberg atoms. Okay, so far we have now really seen that electronic excitation can exert mechanical force on ultra-cold atoms and move them coherently in a controlled way. One can even have entanglement transport in this Newton's cradle kind of motion. And we can have fast electronic coherent transport across conical intersections in ultra-cold gas. And just to give you an idea what we would like to achieve in the long run, we would like to kind of construct molecular type of networks with ultra-cold Rydberg atom chains and configurations. But for that, of course, you need something like reflectors to store the excitons. And you also would like to have switches to direct the excitons at these basically 2 chains which come together. Now, why is it important to have reflectors? And then this you saw already, because once you come at the end, and I'll show you that again with a different color code, once you come at the end, to the end of the chain, then your excitation immediately decoheres across the entire chain. Now it's nicely 2 by 2 still, yeah, 2 by 2. Now we come at the end, and you see all of a sudden everything gets colored. Yeah? So that means we have delocalization of our excitation, and that's not what we want if we really want to transport our excitation. And since we cannot have an infinitely long chain, we need to have something to store the exciton. And so we thought, how can we store the exciton? The most primitive way is to say, let's put 2 stopper atoms at the end of our chain. So these can freely move these atoms along the line as before. And these 2 are in perpendicular traps, so they cannot move in this direction. And they kind of stop the excitation. And this actually works, at least to some extent. This is shown here now. So here on the left-hand side, you see the position of the atoms. This is the excitation on each atom. And this is basically propagation, again, of our adiabatic exciton state, but decomposed, of course, in the amplitudes on each atom. And this is the corresponding potential as a function of time. And you see already here, quite clearly, this must be when it comes to an end, yeah, where the stopper atom sits, it gets kind of a high potential where it cannot go through, it gets reflected. And this is indeed the case, as you can see here. Oops. So it moves on the right hand side and moves nicely backwards. Yeah, and here comes again to the boundary, high potential, moves backwards again, comes to the boundary and moves backwards again, and so on. And this is of course too good to be true, and this is cheating because this is only one trajectory, one nuclear trajectory. This of course does not have dispersion of the wave packet and things like that, so this would go forever. It shows that in principle it can work, but now one has to find the conditions under which it can work, and there we have not been completely successful. Here you see what actually happens as a function of time. Essentially, this is the purity of the entanglement which goes down, and the reason is that you get more and more ionization of your atoms. And the ionization we could suppress pretty well in the freely moving excitation of the chain, as I showed you before, by adjusting the width of the nuclear wave packet appropriately. This is very important. But now we are in a dilemma because we have now two basically conflicting needs, so to speak. In order to have basically a good propagation property, so everything stays coherent along the chain, we need a large width of the wave packet, and in order to have a good reflection property, we need a small width of the wave packet. Yeah? So we need a compromise, and therefore the storage doesn't work so well yet.